Definition of linear combination of vectors. A vector like V in a vector space like V is a linear combination of vectors u1, u2, u3, uk in V when V can be written in the form of C1U1 plus C2U2 plus the rest of the terms plus CKUK. And note that C1, C2, CK are all scalars or real numbers. So that's how we define a linear combination. You don't see any multiplication between U1 and U2. So vectors are not multiplied together. You have some numerical values that are multiplied by vectors, and then those terms are added together. This is basically linear combination. For the set of vectors in the space, like S, the very first vector is 1, 3, 1. The second vector is 0, 1, 2. The third vector is 1, 0, negative 5. V1 is linear combination of V2 and V3. Why? By inspection, everybody. V1 can be written as 3 times V2 plus V3. So this is pure inspection. 3 times 0, 1, 2, plus 1, 0, negative 5. So I'm multiplying 3 by V2 plus V3. It's equal to 3 times 0 is 0 plus 1. I get 1 back. 3 times 1 plus 0 becomes 3. 3 times 2, which is 6, minus 5 is 1. Hey, this is my V1. My V1 is just right here, which can be written as a linear combination of these two vectors. The question says, hey, write the vector W, 1, 1, 1, as a linear combination of vectors in the following set. So in this set S, I have 3 vectors, 1, 2, 3, 0, 1, 2, negative 1, 0, and 1. And I ask you, hey, this is a vector with components 1, 1, and 1. Write this guy as a linear combination of these 3 vectors. So let us begin. Our goal is to find those C1, C2, C3, or scalars such that the W, which is 1, 1, and 1, can be written as C1 times V1 plus C2 times V2 plus C3 times V3. Okay, how do I solve this? We can basically distribute C1 into the parentheses, C2 into the parentheses, or basically scalar multiplication, and C3 into parentheses. What happens? It becomes C1, comma 2C1, comma 3C1 plus C2 times 0, which is 0. C2 times 1 becomes C2. C2 times 2, 2C2 plus, now just distribute C3 into parentheses. You get negative C3, comma 0, comma C3. Okay, what's next? This is equal to, now I'm just combining the first entries, C1 plus 0 minus C3. Gives me the very first entry here. Then 2C1 plus C2 plus 0 is the second entry. 2C1 plus C2. This guy is just 0. And finally, the last entries. You have 3C1 plus 2C2 plus C3, which is the last entry in this vector. Okay, what's next? I found these combinations. Now you need to form the system of equations that you learned in chapter 1. C1 minus C3 is equal to the very first component, which is just 1. Then 2C1 plus C2 is equal to the second component, which is 1 again. And finally, 3C1 plus 2C2 plus C3 is equal to the last component, which is 1 again. So we basically form 3 equations in 3 variables. You have a system of linear equations that you can easily solve. Let us use Gauss-Jordan elimination and then form the augmented matrix. The very first row is 1, which is the coefficient of C1, 0, which is the coefficient of C2, -1, which is the coefficient of C3, and 1, which is the constant term on the right-hand side. The second row is 0, 1, 2, and -1. And let me see. And 0, 0, 0. This is, I guess, simplified version. Yes. We simplified the system of linear equations, which had 1, 0, -1, and 1, and then 2, 1, and 0, and 1, and then you had 3, 2, 1, and 1. So using Gauss-Jordan elimination, we calculate the matrix, reduce the matrix in this form. But take a look. This system has infinitely many solutions. Why is that? Because I have C1 minus C3 equals to 1. From the second row, I have C2 plus 2C3 equals to -1. So here I ended up with 2 equations and 3 variables. I have 1, 2 equations and 3 variables. So I have to use a parameter. For example, I can take C3 to be called T. So C3 is called T now, everybody. T is any real value. So basically C1 is 1 plus T, and C2 is equal to -1 minus 2T. And T is any real value, just a parameter. Here we go. So the system has infinitely many solutions. What's the meaning of that? It means that if, for example, I take T equal to 0, C1 is 1, C2 is -1, and C3 is 0. If I take T equals to 1, I can find other values for C1, C2, and C3. If T is 1, C1 is 2, C2 is -3, and C3 is 1, right? So you get different values when you plug in different T values. So basically, W can be written as, for example, this is just one of the combinations out of infinitely many combinations. You have 2V1 minus 3V2 plus V3. You can plug in T equals to -1 and get other C sub I values, all right? Other choices for T would yield different ways to rewrite W as a linear combination of V1, V2, and V3. So basically, you can write W as a linear combination of these 3 vectors here, and you have different choices. Now that we define the linear combination, we are interested in defining something new, the definition of spanning set of a vector space. Suppose you have a set like S that includes some vectors like V1, V2, V3, Vk, and so on. And it's subset of a vector space like V. We say that this set is a spanning set of vector space V when every vector in V can be written as a linear combination of vectors in S. In this case, we say that, hey, this set spans the vector space V. So you just need to have a bunch of vectors that any vector in V can be written as a linear combination of these vectors. A very basic example is when you have space, these 3 vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 basically span the space. Why is that? Because if I take any random vector like u1, u2, u3, it can be written as u1 times 1, comma 0, comma 0 plus u2 times 0, 1, 0, and u3, 0, 0, and 1. Basically, it gives you the same vector. Here, another example for you. The set like S, including 1, x, and x squared, spans P2. Remember that. P2 is all the polynomial functions of degree 2 or less. All right, that's why we write it this way. A plus bx plus cx squared. So any polynomial in this vector space can be written as P of x can be written as A times 1. This is your very first vector here. B times x, the second vector. And here you have C times x squared. So basically you have A plus bx plus cx squared. So two examples, very basic examples for you to understand the definition of span of a vector space. So you're basically taking vectors and you're going to write down any other vector as a linear combination of those vectors. So again, for Px, we have P sub 2, which is the vector space of all polynomial functions of degree 2 or less, which was defined as A plus Bx plus Cx squared. We can basically take some scalars, A, B, and C, and multiply those by these vectors, 1, x, x squared. These are not usual vectors that you saw in calculus. These are new objects, new representation for vectors, but we need to accept that these are vectors. So this is vector 1, vector x, and vector x squared. And if you just do the multiplication, you get px back. So what is a spanning set for the space? We want to show that this set, S, including three vectors, 1, 2, 3, 0, 1, 2, negative 2, 0, 1, spans the space. What's the meaning of that? It means that if I take any random vector from the space, I can write that as a linear combination of these three vectors. So let us begin, everybody. Let the fun begins. Suppose I take a random vector in the space, u1, u2, u3. Our goal is to find these scalars, c1, c2, and c3, such that u1, u2, u3, or this vector u can be written as the linear combination of these. So c1 times 1, 2, 3 plus c2 times 0, 1, 2 plus c3 times negative 2, 0, and 1. What are those c values? Well, the easiest way is just to distribute c1 here and then distribute c2, distribute c3, and then combine them together as you saw in previous example. It shouldn't be that difficult for you. You should feel absolutely comfortable about these operations. So c1 plus 0 minus 2c3 becomes the very first element here. And then 2c1 plus c2 plus 0 becomes the second component, 2c2, 2c1 plus c2. And finally, 3c1 plus 2c2 plus c3 is the last component that you have here. Here we go. Let us form the system of equations. So remember that two vectors are equal to each other if their corresponding components are equal. c1 minus 2c3 is u1. That's how you end up with this equation. 2c1 plus c2 is u2. And then 3c1 plus 2c2 plus c3 is u3. Okay. The coefficient matrix of this system has a non-zero determinant. It is equal to -1. So it follows that the system has a unique solution, all right? Remember that when you had a x equals to b, if the determinant is non-zero, basically you can find the inverse of this matrix. So the inverse of the matrix multiplied by the left-hand side and right-hand side, inverse of A times AX is equal to A inverse B to basically get a unique solution, everyone. A inverse times B, here we go. So we can get rid of this because the multiplication here, identity matrix. So that's how you end up with a unique solution, because the inverse of the coefficient matrix multiplied by B, which is U1, U2, U3, is basically the solution that you have. So any vector in the space can be written as a linear combination of the vectors in S. And you can conclude that the set S spans the space itself. Perfect. Let us go to the next slide, everybody. A set that doesn't span space. So from previous example, we know that this set, including 1, 2, 3, 0, 1, 2, -1, 0, and 1, has a linear combination. Remember, we did a linear combination between these vectors. It doesn't span R3. Why is that? Because 1, -2, and 2 is in the space and cannot be written as a linear combination of these vectors in S. So not all sets that you see form a spanning set for a vector space. We should be able to write any random vector as a linear combination of the vectors. Definition of the span of a set. Suppose you have a set like S, V1, V2, V3, Vk, which is a set of vectors in a vector space like V. Then the span of this set is the set of all linear combinations of the vectors in S. So again, here you have a set with some vectors in it. You're going to take all possible linear combinations of the entries of the vectors in that set, and you're going to call it span of S. C1, V1 plus C2, V2 plus ... plus CK, VK, and CIs, they are all real numbers. The span of S is denoted by a span S or a span. We're going to list the vectors that you're using to create linear combinations. When span of S is the same as vector space V, it's said that V is spanned by these vectors. Or another terminology is that S, this set that you have here, basically spans the vector space V. Okay, now that we have this definition, we're going to introduce a theorem and another definition for you. Theorem, a span S is basically a subspace of the vector space V. So a span of S is the set of all linear combinations. Those linear combinations form a subspace of V. What's the meaning of that? It means that it is closed under addition and scalar multiplication. So if S, including V1, V2, V3, and Vk, is a set of vectors in a vector space like V, then the span S, which is all possible linear combination of these vectors, is a subspace of V. Moreover, span S is the smallest subspace of V that contains S. In this sense, every other subspace of V that contains S must include all of those linear combinations as well. Now the definition of linear dependence and linear independence. A set of vectors like S, including V1, V2, V3, Vk, in a vector space V is linearly independent if, when you write the linear combination and set up the equation equal to 0, you only have trivial solutions. What are trivial solutions? C values, C sub i's, must all be equal to 0. Otherwise, we say that, hey, they are linearly dependent. So linearly independent if all of these C becomes 0. Linear dependent, it means that you might end up with at least one non-zero value. Perfect. Example of linearly dependent sets. Consider the following set. The set including 1 and 2, 2 and 4 in the plane is linearly dependent. Why is that? Hey, if I just write linear combination of -2 multiplied by 1 and 2 plus 1 times 2 and 4, this guy becomes 0. So I found C1, which is non-zero, and also this invisible number is 1, C sub 2. So C1, V1 plus C2, V2 is 0, but C1 and C2 are non-zero elements. So these two are linearly dependent. This set, 1 and 0, 0 and 1, -2 and 5, in the plane is linearly dependent. Why is that? I can multiply 2 by 1 and 0. I can multiply -5 by 0 and 1, plus the last vector, which is -2 and 5. So you have 2 plus 0 minus 2, which is 0. Then you have 0 minus 5 plus 5 equal to 0. So again, I found C1, which is non-zero. C2, which is again non-zero, and this invisible number C3 is 1. They are all non-zero entries. They are non-zero numbers. I multiply each one of these by these vectors, and the outcome is equal to 0. So since these are non-zero entries, it means that these vectors are linearly dependent. Another set for you, 0, 0, 1, and 2 is linearly dependent. Why is that? Take a look. 1 times 0 and 0 plus 0 times 1 and 2 is equal to 0. I found C1, which is 1, and C2, which is 0. So I don't have any issue with C2, but C2 is 0. But I have issue with C1. C1 is equal to 1 multiplied by the first vector plus C2, which is 0 times the second vector, gives me 0 back. But C1 is non-zero. So these are all linearly dependent vectors. Testing for linear independence. Determine if the following set is linearly independent or linearly dependent in the space. So the set has vector v1, v2, v3, which are 1, 2, 3, 0, 1, 2, -2, 0, and 1. So let us begin, everybody. To test for linear independence or linear dependence, we need to form the linear combination C1v1 plus C2v2 plus C3v3 equals to 0 vector. If all of these Ci's become 0, then you have linear independence between them. Otherwise, you say that, hey, They are linearly dependent. So let us begin. C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, and 1 must be equal to 0 vector. So you end up with 0, comma 0, comma 0. Now you're going to distribute C1 into parentheses, multiply C2 by each component, multiply C3 by each component, and then combine them together. You get C1 minus 2C3, comma, 2C1 plus C2, comma, 3C1 plus 2C2 plus C3 equal to 0, 0, and 0. So two vectors are equal to each other if and only if their corresponding components are equal. You get C1 minus 2C3 equal to 0. The very first components are equal to each other. So this guy is equal to 0 here. And then 2C1 plus C2 is equal to 0, which is this guy here, equals to the 0. And then you have 3C1 plus 2C2 plus C3 equal to 0 as well. So this is your last components that are equal to each other. Very good. Now what? We can form the augmented matrix of this system and then reduce this. So the augmented matrix is 1, which is the component, which is the coefficient of C1, 0, coefficient of C2, negative 2, which is coefficient of C3, and the other side you have all 0 constant. 2 is the coefficient of C1, 1 is the coefficient of C2, and 0 is the coefficient of C3, and you have 0. Then 3 coefficient of C1, 2 coefficient of C2, 1 coefficient of C3 is equal to 0. So you can reduce this. Hey, the pivot must be equal to 1, and everything below 1 must be equal to 0, and the same for this guy here. So let's see. If you reduce this matrix, you get the following identity matrix, and then this guy is equal to 0. What's the meaning of that? It means that C1 must be equal to 0, C2 must be equal to 0, C3 must be equal to 0. So basically found all of those CI values that are equal to 0. So you basically have trivial solution. It means that all these vectors are linearly independent from each other. Testing for linear independence and linear dependence. Let S be the set of all vectors v1, v2, v3, vk, be a set of all vectors in the vector space like V. To determine if S is linearly independent or linearly dependent, use the steps below. From the vector equation C1, v1 plus C2, v2 plus CK, vk equal to 0, write a system of linear equations in variables C1, C2, and CK. Determine if the system has a unique solution or not. Remember that if your matrix is invertible or non-singular, the determinant of the matrix is non-zero, then you can easily work with the system by multiplying the system by the inverse of A and check to see if you end up with a unique solution or not. If the system has only the trivial solution C1, C2, C3, CK equal to 0, then for sure you can say that S is linearly independent. If the system also has non-trivial solutions, then S is linearly dependent. So these are the steps that you saw in previous examples. This is just a summary. Testing for linear independence. Determine whether the following set of vectors in P2 is linearly independent or linearly dependent. So the very first vector is just a polynomial of degree 2 and s. The second vector is another polynomial of degree 2 and less. The third vector is a polynomial of degree 2 or less. Now, you need to form C1v1 plus C2v2 plus C3v3 and set it equals to 0 vector. So C1 multiplied by 1 plus x minus 2x squared plus C2 multiplied by 2 plus 5x minus x squared plus C3 times x plus x squared. On the right-hand side, you have 0 vector. 0 vector in this vector space is 0 plus 0x plus 0x squared. So every little detail is important. Now, if you distribute C1 into parentheses, you can combine the constant terms. So this guy is C1 plus 2C2. And here you don't have any constant. You only end up with linear term and quadratic term. So you have C1 plus 2C2 must be equal to 0. Then for the second combination, C1 times x plus 5C2x plus C3x, it is equal to 0 as well. So as you can see, you need to combine the coefficients together. These are all linear terms. C1 plus 5C2 plus C3 times x is equal to 0 as well. Finally, you're going to combine the quadratic terms together. Negative 2c1x squared plus negative c2x squared plus c3x squared must be equal to 0. Or if we combine, or if you factor out x squared or combine the coefficients, it is negative c1 minus c2 plus c3, which is equal to 0. So let us begin. C1 plus 2c2 is 0. C1 plus 5c2 plus c3 is 0. Negative 2c1 minus c2 plus c3 is equal to 0. So you have 3 equations and 3 variables. You can easily form the matrix. You have 1, 2, 0, and 0, which are the coefficients of these variables. Your variables now are CIs. You get 1, 5, 1, 0, and finally you have negative 2, negative 1, 1, and 0. You're going to reduce this any method that you feel comfortable. So you have 1, the pivot, everything below 1 must be equal to 0. So you can multiply the first row by negative 1 and add it to the second row. Multiply the first row by 2 and add it to the last row. After doing these, reducing the steps, you end up with this matrix. You have a 1, everything below 1 is equal to 0. You have a 1 here, everything below 1 is 0. And then please note that your last row are all equal to 0. But we need to check these as well. If you form the system of equations, you end up with the following C values. C1 plus 2C2 is equal to 0. C2 plus a third C3 is equal to 0. All right, so you get C1 plus 2C2 equal to 0. C2 plus a third C3 is equal to 0. This implies that the system has infinitely many solutions because you end up with 2 equations and 3 variables. So again, you have C1 plus 2C2. You have to introduce a parameter like t or s. It doesn't matter which one you're using. But since you have a parameter, you end up with infinitely many solutions. And from the second line, you have C2 plus a third C3 equal to 0. You can basically say that, hey, I'm going to take C3 as t and write C2 in terms of C3, which is t. And then since this is written in terms of t, you can write C1 in terms of t as well. So you end up with infinitely many solutions and the system must have non-trivial solutions, right? That depends on T. And you can conclude that the set S is linearly dependent because you get C values that are not zero. So that's how you show the system has infinitely many solutions or unique solutions and so on. So if you, for example, take one value for T and get your C values, one of the combinations, this is one of the linear combinations, is 2 times the first vector minus 1 the second vector plus 3 times the third vector equal to 0. You can take this guy, anything else. You can take this guy to be, for example, 6 for simplicity. If C3 is equal to 6, then C2 becomes -2. And then here you get C1 minus 4 equal to 0, and this guy becomes 4. So you get another linear combination of V1, V2, V3, which is equal to 0, but these C values are non-zero. So basically show that they are linearly dependent because you found C values that are non-zero, and you can write a polynomial of degree 2 or less as a linear combination of these. And then if you form the linear combination of these and they set it equal to 0, you can find C values that are non-zero. Testing for linear independence. Determine if the set of vectors in the world of 4x1 matrices is linearly independent or dependent. Well, take a look. I have this set V1, V2, V3, and V4, and you have some column matrices. You want to check to see if they are linearly dependent or independent. It doesn't mention anything to find C values or not, but let's take a look at this. What are the steps that we're going to take? From the equation C1V1 plus C2V2 plus C3V3 plus C4V4 equal to 0, we can rewrite this as C1 times the very first column matrix, which is your first vector, plus C2 times the second vector, plus C3 plus the third vector, and C4 times the fourth vector. And on the right-hand side, you have the 0 vector, which is basically a column matrix. Okay, so let us form the system of linear equations using C values. So basically, you're saying that, hey, C1 plus C2 plus 0 C3 plus 0 C4 is equal to 0. So this is your very first equation. Then you're going to say that, hey, C1 times 0 plus C2 plus 3C3 plus 1 C4 is equal to 0. This is your second equation. The third equation, negative C1 plus 0 C2 plus 1 C3 plus negative 1 C4 is equal to 0. And finally, 0 C1, 2 C2, negative 2 C3, 2 C4 is equal to 0. So we form this system of linear equations. You have 1, 2, 3, 4 equations and 4 variables. If you use Gaussian elimination to show the system how many solutions it end up having, you're going to see that it only has trivial solutions. How are you going to do that? So let us form this matrix. Shouldn't be that difficult. You have a 1, you have a 0, just basically listing all these entries here. And then here you have 1, you're having the column matrices, and you're going to list all of the entries. Then you have a 0, then you have a 3, 1, and -2. Then what else do we have? We have this guy here, which is 0, 1, -1, and 2. So if you form the augmented matrix, you end up with 0, and 0, and 0, and 0. Okay, here we go. This is our matrix, right? So if you add the first row and the second row, this guy becomes 0, this guy becomes 1, this guy is 1, and this is -1, and this is just 0. And so the rest of these are all 0. Now look at the pivot here, it is 1. If you multiply this guy by -1 and add it here, you get 0, you get -3, and you get -1 here. Then your second row, if you multiply it by -1, this guy becomes 0, and this guy is -2 now, and this is -2. And finally, let us take a look at this guy here. Multiply it by -2 and add it here. This guy becomes 0, -6, -2, get -8, then -2, and this is equal to 0. So one by one, we get rid of all of these entries. You can divide this guy by -2 and make it equals to 1, and then simplify it as much as possible. So basically, after elimination, you're going to see you end up with C1, C2, C3, and everything else equal to just 0. So since you have trivial solutions, it should be linearly independent. So again, for these steps, you should feel comfortable about calculating each step in elementary row operations, or if you want to apply elementary column operations, that's absolutely fine. It doesn't matter which method you're using. So if you want to find the determinant of the matrix here, it doesn't work in this case, all right? What are we seeing here? We have this coefficient matrix. You can only work with the coefficient matrix instead of working with augmented matrix, am I right? So if you find the determinant of that coefficient matrix, if the determinant is non-zero, then you can basically multiply both sides by the inverse of the matrix. And then you have the unique solution. That's the whole goal. So this is what we're looking for. If the determinant is non-zero, so if you find the determinant of this matrix, then you need to multiply left-hand side and right-hand side by the determinant, and you get the unique solution. And hopefully that unique solution is equal to 0. So if the unique solution is equal to 0, then you have trivial solution. It means that this guy is linearly independent. Two vectors like u and v in a vector space V are linearly dependent if and only if one is a scalar multiple of the other one. It's a nice criteria for us, everybody. For example, consider these two vectors, 1, 2, 0, -2, 2, and 1. These two vectors are linearly independent because v1 and v2 are not scalar multiple of each other. For example, you can do the division. You can say that, hey, 1 divided by -2 is not equal to 2 divided by 2. I'm just dividing x components, y components, and z components. 0 divided by 1. So there is no way these fractions are equal to each other. So since these fractions are not equal to each other, it means that they are not linearly dependent. So they are independent from each other. So these two vectors, they are not in the same direction. What about these guys? These guys, 4, -4, -2, -2, 2, and 1. So if you do the division here between the components, for example, 4 divided by -2 is -4 divided by 2, which is basically can be written as, now I'm dividing z values, -2 over 1. These fractions are all equal to each other. All right. So since they are equal to each other, it means that they are linearly dependent. So they are all located on the same line, but in the different directions. So here you have these two vectors, right? They are they are not in the same direction. They are not located on one line, but these vectors, they are all on the same line in the opposite direction. So they are linearly dependent. These are linearly independent. We can basically go back and find C sub 1, C sub 2, and then find those linear combinations and show that for the first one, all of those C sub i's are equal to 0. For these, you can find C sub i's that are non-zero. Prove that the set of vectors is linearly independent. So take a look. You have 1, 1, 1, 1, 1, 0, and you have 1, 0, 0. What are we going to do? We're going to form the matrix, right? Now this is what you're going to see using the matrices. The matrix in row reduced form can be written as the identity matrix. Now, C1 times 1, 1, 1 plus C2 times 1, 1, 0 plus C3 times 1, 0, 0 is equal to 0, 0, 0. Or basically, since we wrote it in reduced form, it means that C1 is 0, C2 is 0, C3 is 0, and then we are done. These are all linearly independent from each other. The vectors also span the space because the coefficient matrix of the linear system is non-singular. So another piece of information for you. Since you're forming the matrix for the vectors, and this coefficient matrix here is non-singular, you can definitely conclude that these vectors basically span the space. Coefficient matrix is non-singular. It means that you have inverse of the matrix. You can multiply both sides by the inverse of the matrix and find the unique values for C1, C2, C3 based off of U1, U2, and U3. Or you can take U1, U2, U3 and write them as the combination of C1, C2, C3, and some other values.